SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustion, Module 5, Combustion and Thermochemistry. So, in this module, we have covered two lectures, that is thermodynamic considerations of combustion, then conservation of energy for reacting systems. Today, we will be dealing with the another important topics, that is lecture number 3 on this module, which will cover adiabatic flame temperature, entropy and Gibbs function evaluation for reacting systems. So, in this lecture we will try to emphasize upon the very fundamental parameter, that is adiabatic flame temperatures for reacting systems. Then we will move on to evaluation of entropy and with a concept of absolute entropy. Then we will see the importance of Gibbs function for reacting systems. So, let me start with the first segment, that is adiabatic flame temperatures. As you know, adiabatic process do not convey any kind of heat transfer into the system or out of the systems. And in fact, when you arrest this heat transfer in a closed system, this will be the typically maximum temperature that we can achieve during some thermodynamic processes. Now, with the viewpoint of reacting systems, what you can see in this figure is that if you imagine that there is a reactor in which there is some fuel is coming at certain temperatures, air is entering into the reactor at certain temperatures, and we get the combustion product out of this reactor at certain pressure and temperatures. And through this process we get heat out of the system, and sometimes we also get the work out of the systems. Now we can imagine a situation that as if you can arrest this, there is no heat transfer is possible into and out of the systems, and there is no work transfer to be possible for this case. And imagine that this reactor is completely adiabatic in nature. And of course, whatever combustion products remains, they remain within this reactor. So, what we can see is that through this reaction process, if we arrest all modes of energy transfer out of these systems, then the temperature within the reactor will increase, and it will increase to a maximum possible extent, and that temperatures we call this as an adiabatic flame temperature, or many times we call this as adiabatic combustion temperatures. So, to summarize these things, what we can say that is that maximum heat transfer during a combustion process can be modeled in a steady state reactor through an adiabatic process. In the absence of work transfer, kinetic energy, potential energy, the energy liberated out of the combustion is transferred to the reactor in two ways. One is through this combustion product, other is heat transfer to the surroundings. Now, the smaller the heat transfer, greater is the energy carried out by the combustion products, and greater will be the temperature of the products. Now, by arresting this heat transfer to the surroundings with proper insulation in the reactor, the energy balance can be modeled through an adiabatic modeling. What it says is that if you know all the details of the combustion products, pressure and temperature precisely, and by arresting all other modes of heat transfer, we can evaluate what is the maximum temperature during a combustion process. So, by definition what we say is that temperature that would be achieved by the products in the limit of adiabatic operation of the reactor is known as adiabatic flame temperature, or sometimes it is also referred as adiabatic combustion temperature. And now, how do you evaluate this concept, or how do you evaluate this adiabatic flame temperatures? The adiabatic flame temperature can be determined by the use of mass and energy conservation principle, in which it is proposed that combustion air and combustion products form an ideal mixture. So, if you do that, we can write down this energy balance equations Q dot Cv by N dot F, that is number of moles of fuel per mole of fuel, minus W dot Cv by N dot F will be Hp bar minus Hr, and that is equal to 0 because we are saying this QCv and WCv to be 0. And in such a situation, what we get is that enthalpy of products and reactions per mole of the fuel are equal. So, this can be given through this summation form. Then what we can write is that for reactant and products, we can write in terms of its enthalpy of formations and enthalpy change. So, from this we can derive one important expressions, that enthalpy change of the products as a function of enthalpy change of reactants plus difference in the summation of enthalpies of formation for reactants and products. So, this is the basic fundamental equations that is used to calculate the adiabatic flame temperature. In fact, if you look at this enthalpy, and if you say that this mixture is treated as an ideal gas, then the enthalpy of the mixture can be represented through this temperature change and the specific heat, and that specific heat has to be evaluated at certain temperature. So, let us see how we can do that. So, there are two ways to view these adiabatic flame temperatures. One can say that the reaction can take place at constant pressure, or the reaction can take place at constant volume. This is similar to a philosophy that constant pressure based combustion in a diesel engine and constant volume based combustion in a SI engine. So, with this we are going to model these adiabatic flame temperatures. So, first case, let us analyze that we are going to analyze a situation where adiabatic flame temperature is reached through a constant pressure process. So, if a fuel air mixture burns adiabatically at constant pressure, the absolute of enthalpy of the reactants at initial state is equal to absolute enthalpy of products at the final states. So, this is the conditions what we derived in our last slide, and this also follows from the first law of thermodynamics. So, the very basic expression that we can see, HR, that is reactants are at initial temperature Ti and certain pressure P. Products are at now reached the adiabatic flame temperature and at P. Then we can evaluate the enthalpy of these reactants, total enthalpy of the reactants and total enthalpy of the products. So, this can be represented as a functional form, like one can represent enthalpy as a function of temperatures. So, these reactants can have many number of species, and these species will have different enthalpies at different temperatures. Let us say all the reactants, when they are at this, they are at initial state Ti, and at that Ti temperatures corresponding enthalpy value of combustion, of course it is negative, that is what this is in positive side and this is in negative side, and this number is this point. Now, when the reaction proceeds, at one point of time the products are completely formed, and when these products are completely formed and the process is completely an adiabatic process, the temperature that it reaches is the adiabatic flame temperatures. And if you draw, just that means at that point of time we expect that the enthalpy of reactants and products should be equal. So, you can draw a horizontal line starting from this initial point, and wherever it reaches this product we can estimate this adiabatic flame temperatures. So, this is all about how you can represent it graphically, but theoretically we can represent these things like for reactants all the enthalpy has to be evaluated at the initial conditions. For products all the enthalpies values will be decided at adiabatic flame temperatures and at that pressure, and which is nothing but the function of the enthalpy of formations and Cp times difference in the temperatures for all the constituents. This is what we view this adiabatic flame temperature for a constant pressure process. Now we will move on to constant volume process, and here the concept is same, but pressure is no longer the same, pressure will not be same, but volume remains same. That means reaction takes at constant volume, we are not allowing, it is like a closed system. So, here the fuel air mixture burns adiabatically at constant volume. The absolute internal energy of the reactants at initial state is equal to the absolute internal energy of the products at the final stage. So, what really matters here is internal energy balance you have to do for reactants and products. Now, here if you look at these reactants, the reactants are at initial pressure Pi and temperature Ti, while products are formed at final pressure Pf and its adiabatic flame temperatures. Then what you do, this normally it is difficult to calculate the internal energy. So, you have to find this internal energy through enthalpy route, because enthalpy data table it is available to us. So, you can get it through enthalpy information. So, U can be written as H minus PV, and pressure you know, because the pressure is a measurable quantity and volume is also measurable quantity. So, that equations when you put H minus PV, and what remains same is your volume remains same. So, it is a pressure difference Pf minus Pi. So, the equation now becomes simple. So, here the similar philosophy, the enthalpy of reactants has to be evaluated at the initial conditions, and for products you have to find it through enthalpy of formation with Cp information and change in the temperatures. Then we also assume that reactants and products form an ideal gas mixtures. So, we can use the ideal gas law. Now, to use this ideal gas law, through this we should be able to correlate the pressure volume as a function of its molar number of moles of reactants and the initial temperatures, and similarly for products number of moles for the products and with its adiabatic flame temperatures. By putting all these things, the working equation now becomes HR for unit HR at temperature Ti Pi minus Hp at temperature T adiabatic and Pf minus R bar into Nr Ti minus Np Tad. So, Ti and Tad are temperatures at initial condition and adiabatic conditions, final temperature, and the Nr and Lp are number of moles for reactants and products. And we can also use them through their mass fraction analysis by converting moles into mass. Okay. So, if you do this, the workable equations becomes through this enthalpy information through their molecular weight for reactants and products. Okay. Now, this is the overall philosophy of adiabatic flame temperatures. If you want to draw certain inferences, what message it gives for a reaction? First thing it gives is that although adiabatic flame temperature is a theoretical number, and in fact it is difficult to achieve in a reaction process, but it gives an estimate that during a combustion process, this combustion process to what extent or what is the maximum temperature that we can achieve during a reaction. So, with reference to a specific fuel at given pressure and temperature of reactants, the maximum adiabatic flame temperature is defined for a complete combustion with theoretical amount of air. Now, we define this adiabatic flame temperatures at two situations, at constant pressure and constant volume. Always we will see that at constant volume adiabatic flame temperature is always higher than that of constant pressure. That is mainly because we are not allowing this heat to go out of the system or the reactor. Although this is a theoretical number, but the measured value of temperature during of combustion products is much below the calculated maximum values. That means always for the reaction we can predict this would be the adiabatic flame temperature, but actual measured value will be always less, even several degrees less. That is because for several reasons. First, once adequate oxygen is supplied by allowing more quantities of air, that means we expect the reaction to be complete or say complete combustions. That means we should be able to supply sufficient quantity of air just to make a complete combustions. So, when you do this, it dilutes the combustion products and thus lowers the temperatures. While modeling adiabatic temperature, we say it is an adiabatic modeling by putting insulations, but through this insulation it is possible to reduce it, but it cannot be eliminated completely. Now, when the high temperature is achieved, for example, when the combustion products are formed and high temperature is achieved, there are some products which can tend to dissociate. Now, when they dissociate, the endothermic dissociation reaction lowers the temperature of the products. So, these are the reasons, but conceptually the adiabatic flame temperature is a simple, but its evaluation requires the knowledge of the composition of combustion products. At this flame temperatures, always the products dissociate and they form many species. Now, having said this, next target that we are going to discuss the concept of absolute entropy. So, previously we have also talked about information during a combustion reaction. We find how enthalpy needs to be calculated, internal energy needs to be calculated. Here we will try to emphasize how entropy will be going to be calculated, and this entropy information will tell us, because entropy word comes from the second law of thermodynamics, and it will tell us whether in which direction the reaction is going to proceed. So, the entropy plays an important role in the quantitative evaluation using the second law. With involvement of reacting system, the main problem that arises is to assign the absolute entropy values with respect to for a datum or certain datum conditions. To these datum conditions for entropy is considered at absolute zero temperatures, and that is nothing but your third law of thermodynamics. So, the entropy value related to this datum is called as absolute entropy. Now, when this absolute entropy is known at the standard state, the specific entropy at other state can be found out by adding specific entropy change. So, this is the expression that is represented here. Now, in a combustion process, how you are going to calculate this entropy? First thing, entropy on a molar basis. If you need to entropy at certain pressure and temperatures, first we have to find out what is the reference entropy, and this reference entropy and pressure reference and temperature it has to be found out through absolute entropy. Yes, that means there you talk about enthalpy of formation. Here we will talk about absolute entropy S0, which is a function of temperature only. There is no requirement of pressure, because the third law of thermodynamics says that pressure has no role at absolute zero. So, that point of time we can say the entropy that is calculated, it is S0 at T, and this other reference state that can be approximated, that is minus R by R ln P by P reference. So, this we can get it from ideal gas through an ideal gas relations. Now, we know that typically reference pressure is known and total pressure will be known, but we do not know the respective composition or mole fractions. So, for entropy of a component I in the mixture can be calculated by knowing its mole fraction. So, this is the workable formula for entropy. Now, when you have information about entropy, then you can make this entropy balance. There are two types of equations for entropy balance. One is control volume at steady state. So, in the other is the closed system entropy. So, when you consider a steady state reactor for a combustion system, we assume that air and products of combustion are assumed to form ideal gas mixture. In this case, for an two inlet single exit reactor systems, they can be expressed in terms of per mole of fuel basis. So, a chemical reaction that takes place, we have fuel and we have air, they mix together with their appropriate molar basis, we get CO2, H2O and N2, and with their respective molar component A, B by 2, A plus B by 4, like this. Now, for this we need to find out the entropy balance. So, entropy balance that can be calculated, if you can recall this entropy balance equations. First is entropy of through heat transfer. So, we have to find the different routes how heat transfer takes place at a given temperatures, and per mole of fuel that can be calculated by dividing it. Then SF, that means entropy of this formation for fuel. Okay. Then in this case other components that are there is like here we have O2, we have N2. So, this number is for this fuel and this number is for O2 and these coefficients are for nitrogen. Similarly, in the right hand side expressions are given as a minus number. So, you can write this, and finally last term refers to the entropy production rate for control volume. And there what we have the information is entropy of combustion of air per mole of the fuel, entropy of the existing combustion products per mole of the fuel. Now, same things when you assign that there is no work transfer, no heat transfer and it is a closed systems, then we can write it as entropy for the closed systems as Sp minus Sr is equal to delta Q by T when boundary heat transfer plus sigma. And then this equation can be for products and reactants, they can be summed up with their respective number of moles. Then and we also can find out the right hand expressions per mole of fuel, and this S bar in the left hand side of the equations can be calculated at given temperature and pressure through information of absolute entropy. And the last segment of this chemical reaction is the Gibbs functions. The word Gibbs function comes into picture when you dealt with the thermodynamic property relations, and in fact this Gibbs function has a very vital or important role in the reacting systems, and this information is also similar to what we do it for enthalpy. So, this Gibbs function of formation of a compound is equal to the change in the Gibbs function for the reaction in which the compound is formed from these elements, and this Gibbs function treatment is almost similar to the what we do it for enthalpies. So, the information that is required is the enthalpy of formation plus enthalpy change. Here also same thing, Gibbs function of formation and Gibbs function change between the any given state from with respect to its reference stage. So, if you can recall this Gibbs function G bar is nothing but H bar minus T into S bar, and this Gibbs function when you calculate they can also be evaluated through this enthalpy route. Through this process we can find out this Gibbs function or with respect to molar basis Gibbs function at given temperature at pressure with knowledge of Gibbs function of formation and this Gibbs function change, and this Gibbs function change can be found out from this enthalpy and temperature and entropy. So, to calculate this Gibbs function we also know the information of enthalpy and entropy. Another point I need to emphasize that this Gibbs function evaluation plays a very crucial role for chemical exergy, and which we will not be covering in this particular course, but chemical exergy is very important point for the learners who are in the areas of chemical engineering. Okay, with this we complete this lecture, and based on this content of this lecture we will try to solve some of the numerical problems. So, the first problem is about this calculation of adiabatic flame temperature at constant pressure and constant volume during a combustion process for a methane air mixture, and the conditions that are given is initial conditions are 1 atmosphere and 298 Kelvin and complete combustion process, but we need the products their temperature is or TP combustion product temperature is 1200 Kelvin. This information is required mainly because all the properties needs to be evaluated at this temperature. To solve this problem, and there are two cases, one is constant pressure case, other is the constant volume case. So, before you do that, first thing that you need to write what is methane air combustions? So, CH4 plus 2 O2 plus 3.76 N2. So, this is air and this will give you CO2 plus twice H2O plus 7.5 N2, 52 N2. Now, for this reaction we know that this is 1 mole, this is 2 mole and here also 1 mole and here 2 mole and this is 7.52 mole. So, case 1 we say constant pressure. So, for the constant pressure we say that H reactants is equal to H products. Now, H reactants they can be calculated by summation of Ni Hi, that is for reactants. And before you go for, we need some data. What is the data requirement? We need to find out this enthalpy of formation and this is kilojoule per kilomole and that is we have to calculate for initial condition at 298 Kelvin. We have to get this because you need summation. For CH4 this value is minus 74831. For CO2 it is minus 393546. H2O minus 241845. Then we have other like N2, it is 0 because they are stable gas. Since they are stable gas at the conditions of 1 atmosphere and 298 Kelvin, so they can be assigned as 0. And for even for other situations like at 2200 Kelvin, we require Cp bar, which is kilojoule per kilomole Kelvin. For CO2 this number is 56.21. H2O because we require only for products 43.87 and 2 33.71. Now for reactants this number is summation of NiHi, all other numbers are 0, N2 and O2. So it is for CH4 and that value is minus 74831 kilojoule and this is for 1 mole, that is Ni is 1. Then for products we say H products, that is nothing but summation of products N I. Here we have to find out HFO plus Cp I times T adiabatic minus initial temperature, that is 298. Now we have to put 1 by 1 each, that is 1 mole. For CO2 we have to write minus 393546 plus Cp 56.21, T adiabatic minus 298, adiabatic is unknown, minus 298. Second term will be 2 mole, we can write the same information for water, minus 241845 plus 43.87 T adiabatic minus 298. Last one is 7.52 mole N2, that is first term is 0 plus Cp times Cp is 33.71, T adiabatic minus 298. So, you have 3 terms needs to be added together, and that is equal to HR is equal to HP. Now, when we equate these things and solving, there is one unknown, that is T adiabatic. So, this number would be 2320 Kelvin. So, adiabatic flame temperature for this methane air combustions is 2320 Kelvin. Now, same data, by using the same data, we are going to find out what is the adiabatic flame temperature at constant volume. So, for constant volume, the working equations we can write as HR minus HP minus R bar into NR Ti minus Np T adiabatic is equal to 0. This is the working equation that we derived in our earlier slides. All the information of HR and HP are known to us. Number of moles, reactants and products also known to us from these equations. Initial temperature Ti is known. So, Ti we can write 298 Kelvin. Adiabatic temperature is unknown, and what is R bar? 8.314 kilojoule per kilomole Kelvin. So, by inserting this values and solving, we can reach that this will imply that T adiabatic flame temperature is 2887 Kelvin. Okay. So, if you can closely write all these equations separately, and in this equation all the parameters are known except the unknown parameters is T adiabatic. So, we can put it and find this. So, if what you see here, T adiabatic at constant volume is greater than T adiabatic at constant pressures. Okay. So, this is about the adiabatic flame temperatures. Now, next question we are going to solve about the entropy evaluation in during a reaction process. So, this problem will give you understanding about entropy evaluation in a closed system. So, to do that, let us first find out what is the reaction. This is a methane oxygen reactions. So, same issue, that is same reaction CH4 plus twice O2. Here it is, there is no nitrogen. So, directly oxygen information is given, will give you CO2 plus H2O, and this H2O will form as a gas form. Heat transfer occurs till the products are cooled to 900 Kelvin. So, you can imagine that the reaction is happening in a closed systems of CH4 and O2, and the products are formed. Initial condition is P is 1 atmosphere, T1 is 25 degrees centigrade, 298 Kelvin, and final product T2 that reaches is 900 Kelvin. P2 we need to calculate what is the final pressure. On top of that, we are find out to heat transfer, because for entropy calculation also we require heat transfer. So, first part we can directly write the equation for closed system. This closed system, when you write UP, that is internal energy for products minus internal energy for reactants, is equal to Q minus W here W is 0 and UP and UR is this. Now this U is nothing but H minus PV, and since we are using this ideal gas, we can write H minus RT. So U information we get through temperature only. So from this we can write Q. What is the final quantity of heat transfer? Q is equal to H for H minus RT for products minus H minus RT for reactants. This product we can write, products are formed CO2 and H2O. We can write them as H bar CO2. Of course, here all are molar values, plus twice moles of twice H2O, twice mole of H2O. So then I will write it as for reactants. For reactants is H bar CH4 minus twice H bar O2. So this is for enthalpy part, plus 3 R bar T1 minus T2. Okay, that is because you have 2 moles here, 1 mole here. So 3, there will be 3 term here, and in fact here also 1 mole and here also 2 moles. So that will be 3 times of R bar into T1 minus T2. Then we have to calculate each of the information for CO2 and H2O. That we have to find through enthalpy of formations. HF bar for CO2 plus delta H CO2 plus twice times HF plus twice delta H O2 H2O minus HF bar plus delta HF delta H CH4 minus twice time HF bar plus delta H bar O2. So each information was given here, plus 3 R bar times T1 minus T2. Now here we need to now try to see which needs to be ignored, and oxygen is a stable component, so HFO is ignored. Delta H is also ignored everywhere except CH4, because that is the reactants and products are at same initial temperatures, CH4 and O2. Then what is does not know is this. So using this data table we need to find this information, and then you calculate Q as minus 745,436 kilojoule. Please refer my earlier slides for these numbers, CO2, delta H value, HFO, and evaluate this value of Q. Second part is final pressure. Now to calculate these final pressures we require the ideal gas equations. For initial state we can write P1V is equal to NR R bar Ti, and final state P2V is equal to N products into R bar Ti, and both NR and NP are same and V is same. So we can find this P2 is equal to T2 by T1 into P1. So we know T1, we know T2 and we know P1. So this number would be 3 atmosphere. So we got the information of P2. Then last part of this is, that is in fact which we emphasized in this particular lecture, how to calculate this entropy. So, entropy evaluation requires that what is the final product entropy and what is the final reactant entropy, that is entropy products minus entropy reactants. So, this will give you the entropy change for this closed systems. Now, this SR is equal to, that is reactants, reactant consists of methane. So, S 1 mole S bar. So, if you write the equation, that is CH4 plus twice O2 gives CO2 plus 2 H2O. So, here 1 mole, 2 mole, 1 mole and 2 mole. So, when you take the information from molar entropy, 1 mole of CH4 to S bar CH4 to be evaluated at initial temperature T1, mole fraction of CH4 and pressure P1 plus twice entropy of O2 at T1 and mole fraction of O2 into P1. Similarly, for products SP, products, this is for carbon dioxide 1 mole to S bar of CO2, products are at temperature T2, mole fraction of products YCO2 at temperature P2 plus 2 moles, then in products also you will have H2O. So, entropy for H2O, that is to be evaluated at temperature T2, mole fraction of H2O at pressure P2. So, all these things we know, P1 1 atmosphere, P2 3 atmosphere, T1 298 Kelvin, T2 900 Kelvin. Okay. Then you have to calculate each individual parameters. Let us say, how do you calculate S bar CH4 at T1 Y CH4 pressure P1. So, you have to get it through absolute entropy route. So, S bar O CH4, that absolute entropy has to be evaluated at T reference minus R bar into ln Y CH4 into P reference, that is divided by P reference. So, mole fraction of CH4 1, P reference gets cancelled and the data value we can find out from the table. So, this number is 186.16 minus 8.314 ln 1 by 3, because this P reference will get cancelled. YCH4 from this reaction is 1 by 3, YO2 will be 2 by 3, YH2O will be 2 by 3, YCO2 will be 1 by 3. So, all these numbers you are known. So, this number you have to now calculate from the data table. Now, similarly, from this other data we can find out S bar O2. This value is 20.5. S bar CO2 entropy, absolute entropy for O2 it is 263.5. S bar H2O, that is 228.3. So, by putting this number and calculating each term, we can find out this entropy change. Delta S as 96.4 kilojoule per Kelvin. Okay. So, in our previous lectures, I emphasized how you are going to calculate change in the enthalpy in a reacting systems. In this particular lecture, through this problem, I have made these calculations that how you are going to calculate the change in the entropy in a reacting systems. Also, we have demonstrated during a chemical reactions what is the maximum possible temperature, and that we calculated as adiabatic flame temperature, one at constant pressure, other at constant volume. So, with this I conclude this lecture. Thank you for your attention.